Hello learners, good morning to all of you. I am Rajat Tiwari, lecturer, University Teaching Department, Chhattisgarh Swami Vivekanand Technical University, Bhilai, and your subject matter expert for this course. In today's session, we will be exploring the topic of leveling, focusing on basic terminology and leveling instruments. We will delve into the fundamental concepts of leveling and the instrument that make precise surveying possible. This session aims to provide you with a comprehensive understanding of the terminology and the instrument, function and significance, ensuring accurate and reliable measurement in your surveying projects. We will be discussing the following points, which include leveling and its importance, basic terminology, benchmark and its types, the level instrument and adjustment of level instrument. So, before going to leveling, we will discuss what is elevation and datum. Elevation is a measurement of how high or a low point is compared to a reference point called datum. This reference point of sea level has an assigned elevation of 0. Points above the datum have positive elevation while those below are negative. The term grade and altitude are sometimes used interchangeably with elevation, but grade is more common in construction, while altitude refers to height above sea level. Now, how to determine this elevation? To find the difference in elevation between the 2 points, we use the process which is called as leveling. This involves measuring vertical distances. In simple cases like a building or wall, a tape measure might suffice. For longer distance, specialized equipment and techniques are necessary. So, we will discuss about leveling methods. Basically or primarily, methods of leveling are direct and indirect. So, what is direct leveling? It uses a level instrument to create a horizontal line of sight and measures vertical distances to points of interest using graduated staff. Then second is indirect leveling, which involves calculating elevations based on measurements like angles and distances, often using equipment like theodolite or barometers. So, why leveling is important? What is the importance of leveling? Actually, accurately determining elevation is crucial for various engineering projects. For example, creating detailed maps of Earth's surface, that is topographic mapping, accurately determining the elevation of various points on Earth's surface to create a detailed maps used for planning and development. Secondly, to design drainage systems and sewer lines, establishing the correct slope for proper water flow, preventing water logging and ensuring efficient waste disposal. Next is to plan excavations and foundation for structure, determining the depth and level of excavations for structures, ensuring stability and preventing structural failures. Next is to build roads, railways and bridges, establishing the correct gradient for safe and smooth transportation, ensuring proper drainage and optimizing construction. Lastly, is to monitor building settlements, etc., monitoring changes in elevation over time to assess the stability of structure and to detect potential issues. Now, we will take some technical definitions which are used in leveling. Referring to this figure, firstly we will discuss about what is level surface. A level surface mirrors the Earth's mean spheroidal shape like the surface of a still lake. It is curved surface where every point is equidistant from Earth's center and is always perpendicular to the direction of gravity, that is plumb line, at each and every point. Next is vertical line. Referring to the figure, a vertical line runs from any point on Earth's surface straight to the center of Earth, often aligned with the plumb line. It represents direction of gravitational pull. Next is level line. A level line lies entirely within a level surface. It is normal, that is perpendicular to the plumb line at all points, maintaining a constant distance from the center of earth. Next, we will be studying about horizontal plane. This is a plane that touches a level surface at any given point and extends outward. It is perpendicular to the vertical line at the point of tangency, creating a flat and even plane. Next is horizontal line. Horizontal line resides within the horizontal plane. It appears as a straight line that is tangential to the level line at any point, extending in a flat orientation. Next is reduced level. The elevation of a point refers to its vertical distance from a reference surface, that is known as datum. In surveying, this commonly referred to as a reduced level. Next is line of collimation. The line of collimation connects the intersection of the crosshairs with the optical center of the objective lens and it continues outward. In leveling operation, this line must remain horizontal to ensure accurate measurements. Next is optical line. This is a line that extends from optical center of the lens objective of a surveying instrument to the center of the eyepiece, ensuring proper alignment for viewing. Next, we will be discussing about axis of the level tube. It is an imaginary line that runs tangentially along the longitudinal curve at the midpoint of the level tube of the instrument. Next is height of instrument. This is very important as this term denotes the elevation of the plane of collimation when the leveling instrument is set up and properly leveled. For example, if the instrument shows a height of 102 meters, it refers to the elevation at which the plane of collimation is set, not the physical height of the telescope above the ground. Next, these three terminologies are very important as we have to use this in our next lectures. First is backside. This is the first reading taken from a known elevation such as benchmark or a previously established station after setting up the leveling instrument. It is essential for establishing a baseline for subsequent measurements and is also known as plus sight. Second one is foresight. It is the last reading taken from a point whose elevation needs to be determined. This reading indicates when it is time to move or shift the level to a new position. It is also referred to as a minus sight because it involves descending to low elevation points. And the third one is intermediate sight. It is a reading taken on any intermediate point between the initial backside and the foresight. This point elevation is unknown at the time of measurement and helps in detailing the contour between points. Next technical terminology is change point, or we can also call it as turning point. It is a specific point used for relocating or shifting the level during surveying. Both foresight and backside readings are taken at this point to ensure continuity and accuracy of the elevation profile being measured. Next is the station. It is any point for which elevation is to be determined. The staff is positioned on this point during measurements. This could be any marked position in the survey area such as points A, B or C in the given figure or provided figure. Next is parallax. Parallax is the apparent shift or movement of the object image relative to the crosshairs in the instrument's eyepiece. It occurs when the image formed by the objective lens does not align with the focus plane of the eyepiece, indicating a need for adjustment to ensure accurate readings. Now, we will be dealing with one of the important technical term in leveling, that is benchmark and its type. So, what is benchmark? Actually, it is a stable reference point with a precisely known location, whose location is already known to us. These benchmarks vary based on their permanency and accuracy, which will be basically are of four types. First is Great Trigonometric Survey, that is GTS benchmarks. These are set up by the Survey of India. These benchmarks are spaced approximately 100 km apart nationwide. Their elevations referenced to the mean sea level at the Bombay port and are indicated on GTS maps. Second one is the permanent benchmarks. It is established by government bodies like Public Works Department. These are located on fixed and well defined structures such as bridge parapets or kilometer stones, facilitating broad and permanent applications. Next is arbitrary benchmarks. These are chosen for temporary or small scaling or leveling tasks and do not correlate to a universal datum. Their primary use is to localized projects where permanent benchmarks are not necessary. And last one is temporary benchmarks. These are utilized for short term projects. These benchmarks marks the end of the day's leveling work and start of the next. They are strategically placed on stable but not necessarily permanent structures like kilometer stones or bridge parapets to ensure continuity. Next is we will discuss about the leveling instrument. A level is the instrument utilized for leveling operations. It is composed of several essential components which we will be dealing by one. First instrument is telescope. It is an optical instrument that enlarges the appearance of distant objects to aid in sighting. The telescopes used in leveling instrument typically come in two varieties. First is external focusing telescope and second one is internal focusing telescope. So, external focusing telescope is commonly found in older leveling devices. These require manual adjustment near the objective lens to focus the image, whereas in internal focusing telescope predominantly used in contemporary surveying equipment. These telescopes allow for focusing without altering the physical length of telescope. A telescope in surveying instrument is alike a Keplerian type telescope featuring two convex lenses mounted inside a tubular structure. The lens located closer to the observer is termed as eyepiece, while the lens positioned towards the object is known as objective. Now, we will deal with level tube. This component ensures the line of sight is precisely horizontal, and third one is leveling head. This part is used to adjust the level tube, ensuring that the bubble remains centered throughout the range. The instrument is supported by a tripod which holds these three major components steady during use. Now, we will discuss about in which principle this telescope works. Referring to this figure, the operational principle of surveying telescope is grounded in specific optical behavior. What it is? When parallel rays of light strike a convex lens, they are refracted and converge at a focal point known as the focus. Meanwhile, the rays passage directly to the optical center of the lens continue straight without deviation. The objective lens creates a real inverted image at the position closer than its focal length. The eyepiece then magnifies this image and presents it upright on the same side as the eyepiece. Next, we will study about crosshairs of the eyepiece. It is positioned within the local range of the eyepiece. The crosshairs intersect where the objective lens forms an inverted image of the target. This configuration not only aligns the image, but also enlarges both the crosshairs and image, facilitating precise observations. Next is focusing a telescope. How we can focus a telescope? The process of obtaining a clear image of an object at the plane of crosshair is termed as focusing. Focusing mainly involves primarily two steps. First one is eyepiece focusing and second one is objective focusing. So, in eyepiece focusing, this step involves adjusting the eyepiece unit either inward or outward to make the crosshairs appear sharp and clear. This adjustment brings the crosshair to the plane of distant vision and is dependent on individual's eyesight. The second one is to objective focusing. Here, the objective lens is adjusted to align the image of the object directly within the already focused crosshairs. This can be accomplished through external or internal methods. Hence, the classification is of two types. Basically, first one is external focusing telescope and second one is internal focusing telescope. First, we will discuss about external focusing telescope. These telescopes focus by physically moving the objective lens or eyepiece externally. They typically consist of two telescopic tubes with the objective and eyepiece mounted on opposite ends. One tube slides axially within the other, adjusted via rack and pinion system connected to the focusing screw. Second one is internal focusing telescope. So, in contrast, internal focusing telescope maintained a fixed distance between the objective and eyepiece. Focusing is achieved by adjusting a double concave lens within a small axially sliding tube situated between the eyepiece and the objective. Also using a rack and pinion mechanism as in like the external focusing telescope linked to the focusing screw. As we have already discussed about parallax. So, what is parallax? Parallax occurs when the image of an object as formed by the objective lens is not aligned within the plane of crosshairs. Any movement by the observer's eye causes the image to appear as if it is shifting in relation to the crosshairs. We will discuss about objective lens. So, the objective lens captures light from the object being observed. It typically consists of compound lens with firstly a front double convex lens made of crown glass, secondly a rear convex lens made of flint glass. These lenses are fused together to their meeting point, forming what is known as achromatic lens. This design helps to minimize optical defect such as spherical and chromatic aberrations. Next is eyepiece. The eyepiece is the part of telescope through which the observer views the magnified image created by the objective lens. It usually includes two plano-convex lenses with equal focal length positioned within a tube. The curved surfaces of these lenses face each other and are spaced apart by a distance equal to the focal length of either lenses. Next important one is diaphragm. The diaphragm in a telescope serves as a frame that holds the crosshairs, which are traditionally made from material like silk, spider silk or platinum wires. It is positioned so that the image formed by the objective lens appears at this plane. There are few crosshair arrangement which we will be discussing. Actually, different configurations of crosshair in the diaphragm help with various readings. For instance, basic setup allow for a single reading per staff position, while more advanced arrangement can provide multiple readings which can be averaged for accuracy. This is particularly useful in a configuration where the telescope includes multiple horizontal wires known as stadia hairs, which facilitate distance measurement via stadia tachymetry. Tachymetric surveying is a topic of surveying in which we will be dealing in later lectures. Next, we will be studying about level tube. It is also known as bubble tube. This component is housed in a brass tube sealed with plaster of Paris containing a liquid like ether or alcohol and an air bubble. The bubble always settles at the highest point of the tube, which is shaped into circular arc. The tube's exterior has graduations that help determine the bubble center, indicating a level state. Temperature changes can affect bubble size and sensitivity of the readings. Next is leveling head. This consists of two parallel plates. First one is the tri-back above and the tri-vet below, which attaches to the tripod. It supports the telescope, connects the level to the tripod and facilitates precise leveling. And the tripod provides a stable base for the level with legs that may end in pointed iron shoes for secure ground placement. The tripod's head features a screw to which leveling head's trivet attaches, ensuring level is securely mounted and stable during use. Next, we will be discussing about the types of level. Basically, there are 4 types of level. First one is dumpy level, second one is Y level, third one is reversible level and last one is tilting level. So, we will be dealing one by one. So, first we will discuss about dumpy level. It is created by gravette. This level features a telescope permanently fixed to its base, incapable of rotation along its longitudinal axis or detachment from its base. It is known for its relatively short stature compared to its magnifying capabilities, hence the name dumpy, which implies short and stout. It includes a long bubble tube atop the telescope and a leveling head with 2 parallel plates and 3 or 4 screws. The upper plate is called tri-back and the lower plate is known as trivet, which is attached to the tripod. Next is Y level. This level has a telescope cradled into 2 vertical Y-shaped supports, allowing for rotation and removal of the telescope. The Y-shaped supports are adjustable, securing the telescope when tightened. Likewise, the dumpy level, it may also feature a level tube on the telescope or the stage and typically includes a similar leveling head with the addition of a clamp and tangent screw for fine horizontal adjustments. Next level is reversible level. Combining features of both the dumpy and Y levels, the reversible level is versatile, using a telescope that mounts into rigid sockets. This setup allows the telescope to function as either type, depending on whether it is locked in place or allowed to be removed and reversed. This dual functionality facilitates easy adjustment and precision in leveling. Next or last one is tilting level. This type of level has a telescope that can tilt a few degrees vertically controlled by a tilting screw. This design is meant for precise measurements where the line of collimation and the vertical axis needs to be perpendicular. Usage involves roughly leveling the instrument using the leveling screws against circular level, then finally adjusting the main bubble tube with the tilting screw to ensure accuracy before each observation critical for achieving precise data. The design ensures the operator can see the bubble tube while sighting the staff, crucial for accurate readings. Now, we will discuss some of the advantages and disadvantages of different types of level which we have discussed earlier. So, first one is dumpy level. So, advantages of dumpy level include that it is simple in construction with minimal movable parts. It requires fewer permanent adjustments, and once adjusted it maintains accuracy for a long duration. Its disadvantage include that it is limited precision compared to other levels, and it may require manual adjustment in the field. Considering Y level, advantages include it allows for quicker and easier adjustment, and adjustments are more rapid, reducing the frequency of checks in Y level. And the disadvantage that it has a large number of movable parts, which can lead to a more frequent disturbances, and adjustment may need to be checked more often. Next is tilting level. Its advantage includes that it allows for precise centering of the level tube during observations using the tilting screw. It speeds up the leveling process by requiring only rough leveling initially. Accurate centering is done with a tilting screw before each reading. Its disadvantage can be more complex to operate due to the tilting mechanism. It requires careful handling to ensure accurate centering. Next, we will be dealing with the leveling staff. So, leveling staff is a straight rectangular wooden rod marked with measurements in meter of feet and smaller divisions. The bottom of the staff indicates 0 reading. The height of the line of collimation above the point where the staff is held is determined by reading the staff through a telescope. Leveling staff are classified into mainly two types. First one is self reading staff and second one is target staff. So, self reading staff is a staff that allows direct reading through the telescope. It are basically 3 or 4 types. First one is solid staff. It is typically 3 meter long in one piece, providing high accuracy due to the absence of hinges or joints, but can be cumbersome to transport. It is mainly used for precise leveling tasks. Second one is folding or hinge staff. It is made from well seasoned timber. This staff is 4 meter long and divided into 2 meter sections connected by hinges. The staff is equipped with brass cap at the foot to prevent wear and may include the plummet for verticality of checks. It is graduated with decimeter and millimeter divisions, and the numerals are marked in red and black for clarity. The staff can be folded for ease of transport or used in parts as needed. Next one is telescopic type staff. This staff consists of 3 pieces. First one is solid top piece of 1.25 meter. Second is the central hollow piece of 1.25 meter and a lower hollow piece of 1.5 meter. When fully extended, the staff reaches 4 meter. The divisions are marked in 5 mm increment with red meter numerals and black decimeter numerals. The staff's graduation appear inverted when viewed through the telescope, and it must be fully extended for accurate use. Second one is target staff. Target staff consists of 2 rods, with the upper rod that is 6 feet long sliding into the lower rod that is 7 feet long. It includes a movable target attached to the staff. So, its operation include that the staff can adjust the target's height until it is aligned with the line of sight. that clamps the target in place for the reading. The staff is graduated in feet with additional divisions for tenths and hundredths. Now, we will be dealing some of the adjustments of the level. Actually, a level requires basically two types of adjustment. First one is temporary adjustment and second one is permanent adjustment. So, what is temporary adjustment? Temporary adjustments are performed each time the level is set up. They include firstly setting up the level, in which we will mount the instrument on the tripod and adjust the leg so the instrument is approximately level. To do this, we have to release the clamp, hold the instrument in one hand and attach it to the tripod by turning the leveling head with other hand. Adjust the tripod legs to achieve a convenient height and ensure the tri-back is roughly level. Modern levels often have small circular bubble on the tri-back to assist with his preliminary leveling. Next is leveling up. That first one was setting up the level and the next step is leveling up, whose objective is to achieve precise leveling. So, the instrument vertical axis is perfectly vertical. It includes the method of three screw head, in which firstly we have to loosen the clamp and align the longitudinal axis of the plate level parallel to a line connecting two of the leveling screws, example A and B as shown in the diagram. Nextly, we have to adjust these two screws uniformly until the bubble in the plate level is centered. Thirdly, we have to rotate the instrument 90 degrees. So, the plate level is now aligned with the line connecting the third screw C and the midpoint of two screws A and B. Next, it is to adjust the third screw until the bubble is centered. Next step is to rotate the instrument back 90 degree to the original position and repeat the adjustment of the first two screws until the bubble remains centered. Next step is to rotate the instrument 90 degree again and repeat the adjustment of the third screw. Then continue adjusting until the bubble remains centered in all positions. The next step is to rotate the instrument to 180 degree. If the bubble stays centered, the vertical axis is now truly vertical. If not, permanent adjustments are needed. And the next step in temporary adjustment is to eliminate the parallax. As we have already studied about the parallax, we will directly go through the steps of eliminating parallax. That first one is to focus the eyepiece, in which we will point the telescope at the sky or a white sheet of paper in front of the objective. We will adjust the eyepiece until the crosshairs appear sharp and distinct. Some eyepieces have graduations that allow you to note the setting for future references. Next and the last one is focusing the objective, in which the aim is to we aim the telescope at the leveling staff and use of the focusing screw to sharpen the image until it is clear and sharp, ensuring the image is in the plane of crosshairs. With this, we can easily do the temporary adjustment. In the next lectures, we will discuss about permanent adjustment. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next lecture. Thank you.